Hola.
Hola, hola.
Hola, hola.
Hello.
Hello. Congrats, Jenny.
Congratulations.
Wonderful talk.
¿Quién está grabando o es automático?
Creo que el profesor graba.
Creo que automático.
¿Por qué no?
Porque no veo a Franz.
Sí.
Sí, creo que automático.
Hola.
Hello.
Hola.
Okay. Any questions before any past lectures? Doubts?
Yes. What kind of detectors we can use in order to measure and study the flux density of the Bremsstrahlung flux density?
Well, depends on what frequency regime we're wanting to study it in.
Low frequency, right?
So, radio telescopes, either single dishes or interferometers, right? You could track it that way. Certainly, the Raleigh Jeans tail, you could do that way.
And more high frequency, higher.
So I mean, you could, in theory, you could see it optically. However, there are other processes which compete and typically dominate. So it's actually pretty hard to see it. It's an interesting question for homework to compare what the flux would be at optical wavelengths for an ionized region versus whatever else is there. I think I actually asked that on some test or homework at some point. But yeah, I mean, you have to compete with starlight, right? So you have the stars, which are actually, in a H2 region, for instance, you have to compete with the UV radiation from the central star. And so typically that may dominate unless the thing is optically thick. So you can't really see it.
Thank you.
And then if you go to the X-rays, right, you need X-ray detectors. So we're just talking about vastly different technologies to detect things.
Yes.
But in theory, we calibrate all that out, all the instrumental stuff. We forget about it and we just measure things in pure flux units or what have you. Never the case, but it's an idea. Okay, I think we're all here now, so let's start. Okay, so we were, as I think, somewhere. So we were talking about the different physical mechanisms that might make Bremsstrahlung or free radiation Bremsstrahlung. We talked about H2 regions. We talked about planetary nebulae. Those are the two main places you will find it, and then also AGN will, have ionized regions as well. But again, typically, as I was saying to Roy, it's difficult to see it in the optical due to the other contaminating radiation you can see. But in the radio, you can often see it. There's a plot I'll show a little bit later to highlight how easy or hard that is. Right, so we talked a little bit about sort of how to calculate this, what the spectrum will look like. And so this is not too bad. But typically, once I think this is not in any sort of actual units, but imagine this was in gigahertz, which is actually pretty typical. So you might see the turnover at a few gigahertz. And then starting at around 100 gigahertz, sort of in the millimeter regime, the dust emission starts taking over. And so that typically washes this out. And then once you go to the near infrared, then you have starlight, which starts to dominate. And so you need a large density, a high density of plasma to compete with that, right? Because this emissivity goes as the density squared. Okay, so I also took just a slight deviation to talk about the spectral index, which is how you measure or how you might differentiate Bremsstrahlung from other mechanisms. And so, so if you have a pure sort of uniform emission of Bremsstrahlung, it'll look like this. So there'll be some portion which is optically thick, some portion which is optically thin, and the break will happen right around tau equals 1. So that's for a uniform sort of effect. The problem is that if you have inhomogeneities in it, you blur this around, and you may also dampen the slope a little bit, so it's not it's not goes as nu to the squared, but it might go as something shallow, because different regions are combining and adding up here. So that's kind of what I was getting at here. So in an inhomogeneous region, we'll have a spectral index here well above this break frequency, so it'll look like that. And it should have something a little bit less than +2 above the break. But if you have a different distribution, right, which is contributing to the density, for instance, a stellar wind, you might have a density which goes as r to the minus squared. And so then you would see a variation as a function of radius away from the star. So the spectral index would change close to the star versus away from it. So one way to quantify this in sort of simple terms is to wrap up this density term in the density along the line of sight is what you kind of want, or it's an easy thing to sort of quantify. And so that's typically this integral here across the line of sight of the density squared is called the emission measure. And so our absorption coefficient is going to be proportional to this n squared, and the optical depth is proportional to the emission measure by extension. So typically you can parameterize the optical depth as a function of the emission measure and the frequency and the temperature, and then our happy Gaunt factor here. And as I mentioned before, this Gaunt factor has a very weak frequency dependence, but it goes to the logarithm, so it's very shallow, and then you have a slight temperature dependence as well. So you often see this as a way of estimating tau. And so if we have if we evaluate these different constants here, we can kind of put it in terms that are relatively easy. So if we can factor in this logarithmic dependence and this frequency dependence, and this is kind of a good approximation. So you see it's very slightly different from 2, and the temperature is very slightly different from 1.5, minus 1.5. And so this is a very easy formula you can just plug in. The typical H2 region might have a temperature of 10 to the 4, so this is 1. You might be measuring the radio, so in gigahertz, so this is a few. And so then you just start caring about this, which is the size of the region and the density squared in that region. Right? And so tau is pretty easily proportional to the density squared. We can also characterize this optical depth in terms of the electron temperature, and we could rewrite this as in terms of the brightness temperature that typically is what you measure in the radio. And so you can see that they're related, but they only actually equal each other when this thing is 0, right? And this thing is 0 when tau is high, right? So for very high optical depths, the electron temperature is equal to the brightness temperature. And so you just measure the flux and the Rayleigh jeans, or the sort of tail of this distribution, and you can get the electron temperature, which is nice. Okay, and actually I forgot to make myself bigger. Okay, so this is sort of useful. We don't necessarily know the structure of H2 regions, and so we can approximate it as a cylindrical geometry, and where we have an axis along the line of sight. And so if we set this axis length equal to the diameter, so it's kind of a squat cylinder, we can get a decent estimate of things. If we then assume that things don't vary strongly across this cylinder, so the temperature and density are constant, then we can pull out physical constraints on the H2 region. So we can get the average electron density, we can get the average temperature, we can get the average emission measure, and therefore we can get the average production of ionizing photons, right? These are all the things you would want to estimate the number of ionizing photons, given this plasma is just made up of hydrogen, for instance. Okay, so it's nice because you can kind of do a circular argument and estimate, what the internal number of stars, the ionizing stars are. So if you have some IMF, some number of stars as a function of mass, you can then track that with the number of ionizing photons, and you then have an estimate of the star formation, right? Because this is telling you the number of ionizing photons, which is related to the number of stars, which is related to how many stars are formed that can emit UV radiation. After a certain time of evolution, the H2 region will, those blue stars will blow up in supernovae, and you will no longer have a source of ionizing photon. So the H2 region disappears. And so there's, over a given span of time, this free emission ends up being a very useful tracer of star formation. We can turn this into so just turning this into a production rate of ionizing photons. So sometimes we call this the free spectral luminosity, where we measure this at high frequencies, so tau much less than 1. This sort of equality will hold. So we have the number of ionizing photons equals this value, which we've sort of calculated out, and we have some luminosity here that we measure in the radio, and at some frequency for some given temperature. And so we could plug in some typical values here. So we have the ISM of the galaxy. There's a diffuse ionized component known as the warm component, which has about a temperature 10 to the 4. And then there's also a hotter phase, which has temperature 10 to the 6. Typically in the ISM, these two are in pressure equilibrium. And so what this ends up meaning is that the hot medium is less dense by a factor of about 100. And so we could estimate what the emission is and how many photons we needed to power these two components. Right, so the combination of a high electron temperature and a low NE of the hot phase means basically only the warm component will contribute significantly to a free opacity, because remember tau goes as to the density squared. Right? So much lower density, it just isn't going to contribute at all. And so this warm ionized gas is confined to the disk. And so there'll be some frequency range in this case where the disk will become optically thick to radiation, right? So just thinking about, come back. So just thinking about this, the entire disk has an ionized component. And so it is susceptible to free absorption. And so the disk becomes opaque because tau becomes very, very large at low frequencies. So we sit in that disk. And so there is some frequency range over which or below which we can no longer see outside of our universe or outside of our galaxy, right? Because we're surrounded by this ionized component. Likewise, the atmosphere of the Earth has an ionized component. And so there are some frequencies that don't pass through the atmosphere at very, very low frequencies. Right? And this is due to free absorption. Okay, so the sort of observed spectral brightness, the observed brightness spectrum in a direction perpendicular disk was estimated to be about, basically through the spectral brightness, it was estimated that tau equals 1 at about 3 megahertz. So below 3 megahertz, typically in a direction perpendicular to disk, we can't see outside of our own galaxy. And so we can actually use this estimate to estimate the electron density in the warm ISM. And so we can plug in tau equals 1. We have our formula here. So this is temperature in units of T to the 4, so it's 1. This is our frequency in units of gigahertz, so this is megahertz, so it's very small. And then we have our mission measure. And the disk height is roughly 1 kiloparsec. So we can move all these over and we can calculate what the average electron density is, right? And take a square root of that. And we end up with a density of about 10 to the minus 1. And so that's the typical density of the warm ISM component. We could also, because we have this volume here, we could estimate what the total mass in the gas, the ISM, is in that component. Right? Fairly straightforward. So it turns out free ends up accounting for about 10% of the total radiation that we see from star-forming galaxies at 1 gigahertz. And so as you move to higher frequencies, it tends to contribute more. And at lower frequencies, it has a cutoff. And so galaxies actually are opaque to it. And so they don't radiate too much at very low frequencies in free. And so typically the strongest component is you'll see is you'll be able to measure the best between 30 gigahertz and about 200 gigahertz. And so that's useful in terms of estimating star formation rates of galaxies, right? And so a typical spectrum, this is M82. And so this is the free emission component you see here. It's pretty faint. This is the dust component. This is the synchrotron component, which we'll talk about in a second. And so, there's a sweet spot here where the free emission actually peaks up and you can measure it. But there, of course, are degeneracies. You have to really nail down this, you have to nail down this, and then you're looking for an excess here. So it's tricky. But people are starting to do that, particularly because radio telescopes are now moving up to being able to observe in this frequency range. Obviously, ALMA can do this at the lowest band of ALMA band 3. There was a proposal deadline this morning, is right around 100 gigahertz. And so ALMA can do this pretty nicely. The VLA goes up to, I think, 40 gigahertz, so we can do it decently as well. Okay, so the last, actually, there's 2 more examples. And I have a phone call. Let's see who that is. No, not a phone call. Just, so this second to last example is branch line from an X-ray cluster. And so Clusters of galaxies were observed back in the 1950s when the Palomar survey started mapping the sky. And they were observed in optical. And people went out and got spectroscopy and estimated the velocities of the galaxies. And the velocities were very high compared to the total mass they could estimate from the galaxies themselves. And so Fritz Zwicky, sort of postulated that there seemed to be some extra matter, some missing matter that was missing in order to explain these high velocities. But people didn't really understand it, and so it just was an oddity and was put away for 20 years. And of course, then Vera Rubin started measuring this missing mass and others, this missing mass via galaxy gas at large radii. And so then we started putting that two and two together. But the point is that the required masses here were of the order of 10 to the 15, which is a huge amount of stellar mass compared to the galaxies, which typically have maybe a baryonic mass, observed mass of sort of several times 10 to the 13 or up to 10 to the 14. So roughly 10% only is counted for by the galaxies themselves, or maybe 5%. So if we had some gas that fell into this sort of potential, the gas would be heated up to very high temperatures in the centers, right? And so the temperatures would be in excess of 1 keV, or about 10 to the 8. Obviously, the gas will be a complete plasma at that point, right? Fully ionized. And so this temperature, exceeds the ionization potential of helium, hydrogen, and actually many metals, oxygen, et cetera. So you'll strip out the outer shell of most metals, even iron, to some extent. We'll have only 2 shells left over in this. This medium is relatively tenuous. It's not that dense, but it's a large volume, and it's much denser than your typical densities of say, the hot or warm ISM. And so it will emit Bremsstrahlung from the core here. And obviously the density will be a function of radius, right? Because of gravitational pressure, the density will be higher here than here. So the emission will peak in the center and have a radial gradient going out. And this is sort of related to one of your problems. And so in addition to the emission, the gas will be able to cool via that emission, right? So it's radiating energy away, and that energy comes from the gravitational pressure, forcing this gas to have a high kinetic temperature. And so by radiation, it can cool and the kinetic temperature can drop. And so we can estimate the rate at which this is cooling. So this sort of rate goes as something like this. And so assuming that we have a hot gas here, it's in hydrostatic equilibrium, fully ionized plasma. So Z equals 1, and these two are equivalent and roughly equal to 10 to the minus 3. We can estimate a cooling time. And that's simply just that, so the energy content of the cluster is related to the number of particles times each particle energy, KT, right? And so the cooling time is just this energy divided by the luminosity, which is related to this emissivity. And so this ratio will give you a cooling time that's roughly about 10 to the 10 years, which is close to the age of the universe, not, just under it. And so what that suggests is that if this sort of was able to exist for most of the universe, it would just barely be able to radiate most of its energy away. And the fact is that most of the clusters were sort of constructed on a time scale over maybe the last 5 gigayears or so, months, where most of the clusters really started forming. and becoming quite large. We do see protoclusters out to redshift 2 or so, which is maybe 8 years away, but that's less than this, right? And so most of the clusters are still kind of relaxing and cooling their sort of kinetic energy away. This is a typical spectrum. It's in weird units, which are instrumental units, which is actually sort of related to Roy's question, or related to the answer I gave Roy. But you have X-ray detectors, and X-ray astronomers love to plot things in terms of detector units, which is what you see here, and that's why it has this weird shape. If you folded out the detector response as a function of energy, then you would see that this just goes like this. And you do see a bump here, and that bump is actually from iron. So there's lines that are in here as well. But the spectral resolution is terrible, so you don't really see those lines very easily. Another place that you see thermal emission is from supernova. So supernova have a kinetic energy in the form of a blast wave, and so the ejecta from the supernova will interact with the circumstellar material. Typically, that's a wind that the progenitor star was shedding before it went supernova. The wind has a typical velocity of maybe 1 to 100 kilometers a second. The ejecta has a velocity of 10 to 5 kilometers a second, and so you sweep up this material, and in the process you shock it. And so you drive a shock through the material. You also drive a reverse shock through the ejecta. And so this is an example from supernova 1987A, showing the HST image, the Chandra image, and the radio image. And this was a weird supernova. You had a ring. And so you had, early on, you had the supernova go off, and the ring is part of the circumstellar medium. It was created before the star went supernova. And the shock is moving out, it's moving out, and you can see here's the shock, here's the shock, here's the shock. It's growing in size in the X-ray and radio because those are directly tracking the shock. And it only hits the ring in 2003 and lights up the ring. So you see all these little nodules where the shock is now interacting with the ring material. And so the X-ray emission goes up, the radio emission goes up as well. And so the spectrum looks something like this, again, in these weird units, but it typically will have a very smooth sort of shape from the bremsstrahlung, but this is mostly material from heavy metals, right? The ejecta is mostly processed nucleosynthesized material. So you see a lot more, stronger emission lines from magnesium, oxygen, silicon or sulfur, not much iron because the temperature is still relatively low, so you don't ionize them. So these strong shocks will drive this ejecta to have extreme, the CM and the ejecta to have extreme temperatures, and of course then they will radiate via bremsstrahlung. They have extremely high densities, and so they end up being very bright because of course bremsstrahlung goes as a temperature to some extent, but also to the density squared. And because these things are sweeping up materials, so a very thin shell, you can have very high luminosities. And so given the densities involved here, typically it takes about 1 year to come into equilibrium. And so at early times, the supernova are actually out of equilibrium, and it is a pain in the butt to calculate what the spectrum is going through because the process of emission and absorption are interplaying, and you haven't fully ionized the region, and so it's sort of complicated. This is actually a movie showing this interaction. So it's basically a movie showing this from one of my colleagues, Vikram Dorkadas. And so this is the density distribution. So you see a huge, this is the shock wave coming out. This is a pre sort of region before the shell. And then this is the shell out here. There's actually a couple of ionized regions here. And you'll see the X-ray and the radioluminosity as a function of how this proceeds. And this is going to go very fast, so sorry. But this is the density and this is the pressure in blue here. Oops, went too fast. Let's see, come back. All right, so you see it goes very fast, and it hits the denser material, and it slows down. I can step through that a little bit so you actually see it. So the shock in the low density material travels very, very fast because there's nothing impeding it, and it sweeps up a little bit of material here, right? So you can see this is the pressure, this is the density. You can see the X-rays are rising, not much radio yet, and then it slams into the H2 region, and you start to see an increase in the X-ray luminosity because the density is increasing, right? And then again, it proceeds, you start to see the radio emission now. It develops a forward and a reverse shock. Then, as it slams into the ring, you see, again, the luminosity start to peak up again, right here, and the radio emission starts to peak up, and it's pretty slow. So the radio emission actually peaks up a lot because the forward shock is moving through, but the reverse shock, which is giving rise to the X-rays mostly, is not doing much yet. And so if you evolve it, you kind of can remain to see that. So the radio emission comes up while the X-ray emission stays kind of flat. So that's the idea behind this. You can use this. You can trace emission lines that trace the velocity structure and so forth. Oops, back before, one slide before. Okay, and then finally we have, an example much closer to home, which is the sun. So the sun has magnetic reconnections, and you can, observe the sun in X-rays, and so you can see the magnetic reconnections. So the surface of the sun is relatively dark in X-rays, but where the magnetic reconnections are, and where you're accelerating electrons, and you're heating up the plasma, which then cools via Bremsstrahlung, you can see very cleanly these regions. Right. Okay. Any questions about Bremsstrahlung?
I have a question. I don't know if you can listen to me for well.
Un perro, pero yeah.
Yeah, sorry. Okay, it's someone that arrived, so my dog is okay. My question is if always when we talk about the Bremsstrahlung emission, we need to consider the absorption, the self-absorption?
Well, you can calculate where tau will be. And I mean, for X-rays, you're typically seeing the Wien side of the spectrum. So, going way back to here, you're typically seeing this end. So you never have to worry about absorption of the X-rays. In the radio, yeah, you have to worry about it. And in particular, I mean, you can look at this example, right? So this is actually a huge density. And so you can kind of see where, there will be a very flat region here. And so, if you could observe the clusters in a range where you could measure tau, yeah, you could do some interesting constraints. But here you're in the optically thin region. Most of the energy is coming out here, right?
Okay.
So if you have a flat spectrum like this, almost all the energy is coming out around the peak, because obviously this is in log scale. And so if you integrate this, you'll see that this has a pivot in energy that comes right around here. And so if you want to measure the overall bolometric luminosity, all you really need to care about is this, because this isn't going to contribute much.
Okay. In that direction was my question, because of the total luminosity that maybe we can measure regarding the previous example of the X-ray star. But okay, thank you.
It would be different if the spectrum was climbing like this, right? Because then you have equal power, potentially on equal decks of wavelength or frequency, and so then you would need to account for everything. And this is kind of one of the cases of AGN where the UV is much brighter than the X-ray, so you need to account for both. Any other questions, thoughts? Okay, so that's Bremsstrahlung, and so that's typically Coulomb interactions between ionized particles. Now, we also have the fact that in ionized regions, you may have magnetic fields, right? And so you will have an acceleration between a charged particle and the magnetic field. And so this will lead to a breaking radiation known as magnetobremsstrahlung, right? And so you obviously have some interesting potential there. And so this sort of, because acceleration, you have acceleration by an electric field, this will lead to free radiation. Acceleration by a magnetic field leads to magnetobremsstrahlung. And so we have any sort of light particles, those are going to be the ones that are affected because they're more easily accelerated than protons. So electrons or positrons, if any actually exist. And so the electrons do all the work, and they're the ones doing all the, the radiation that we observe. So depending on the speed of the electron and the strength of the magnetic field, there are several regimes of magnetobremsstrahlung. And so at the low regime, where you have electrons with velocities much smaller than the speed of light, you typically have something called gyro radiation. When you start to get to electrons which are mildly relativistic, so they have energies similar to their own rest energy, these emit in synchrotron. And then when you have ultra relativistic, when kinetic energy is much less than the rest energy, you have cyclotron, but still, a fraction of the speed of light or something. And then when the kinetic energy actually equals the rest energy, then you end up producing synchrotron. And so, I think people are most familiar with synchrotron, because it's a beamed radiation, and so it ends up getting a boost from that. And so synchrotron, of course, accounts for the bulk of the radio emission from AGN, although there is some free emission, as we just mentioned. It also tends to dominate the emission from galaxies. And, I showed you the spectrum of M82, a star-forming galaxy, and you saw that the synchrotron radiation actually was above the free for most of the radio spectrum. So what's actually going on? We can calculate this pretty simply. So we solve the equation of motion for the particle. We have, particle of mass m and charge q. It's in a magnetic field. We can use the relativistically corrected equations. So we have this time derivative here of the sort of energy is going to be related to this dot product. This is 0, and then we have the time derivative of the relativistic momentum. This is going to be related to velocity cross product with b. And so this is where all the interesting stuff happens. So if we assume that we have a constant set of electrons here, so this is constant, and that the velocity, the absolute value of the velocity is constant, then we can rewrite this equation as something a little bit simpler like this. This is the acceleration. And so we can separate out this velocity term into parallel and perpendicular. And it turns out that the parallel component is going to have a time derivative of 0. And the perpendicular component is going to have a non-zero component, which is related to the actual velocity cross product with the magnetic field. So it's, again, what we're seeing is in this sort of perpendicular direction to the velocity that this is traveling. That's where we're going to have this sort of change come from. So this thing is constant and this thing is constant. That also means that this thing will be constant. And so this then becomes relatively easy to solve. And so we have a uniform motion in normal plane. So it's just going around like this. And because there's also a velocity in the parallel component, we actually see a helical motion. Right, so it's going to look something like this. So magnetic field in this direction, velocity in this direction, parallel component, perpendicular component, acceleration inward. And so we will end up seeing helical motion go like this. The frequency of this helical motion, or this gyration as it is the synchrotron orbital frequency. Someone's phone is going off. Let's see. Oh, weird, I can't. There we go. Okay, so this orbital frequency is going to be related to the charge, the magnetic field, and this gamma factor. And so we can redefine this as this frequency, the Bremsstrahlung, magneto-Bremsstrahlung frequency, times, well, basically there's a gyro frequency, which is just these portions, and then gamma. And so the gyro frequency ends up being independent of velocity. So it's kind of an intrinsic property of the region. So it just depends on the charge, which is more or less constant for an electron. It depends on the magnetic field, which isn't, but that's the only thing that it depends on. And then we have these two constants. And so we can split these out. So the gyro frequency will equal the actual frequency only when V is much, much less than C, and gamma therefore goes to 1. But when gamma is large, this frequency is lower or faster than this one. Sorry, not faster, slower. Yeah, so if we calculate this out, this gyro frequency equals something like 17 or 18 times 10 to the 6 rad per radian per second times the magnetic field. And so typically we can write this also as a frequency just by converting by 2 pi. And so we can estimate the gyro frequency in megahertz. And so as a function of the magnetic field, it's roughly going to be about 2 to 3 or 2.8 or 3 megahertz. And so thinking about the Milky Way typically has a magnetic field of about 5 microgauss. Yeah. And so this gyro frequency will end up being about 14 hertz. So it's very, very low. So this is, this is the frequency at which this is moving around. Because this thing has a, some sort of change in its accelerating, we can calculate a power associated with it, right, via the Larmor formula. And of course, the Larmor formula has a, you can turn that into, by Fourier transform, you can turn that into a, the time dependence equals the frequency dependence in terms of spectral frequency. Because this has a very uniform frequency of oscillation, what you're going to do when you turn it into an actual frequency is it's going to be an emission line, right? Because it has a very specific frequency. When in the non-relativistic case. So basically this radiation field will vary at the same frequency as deceleration. And this typically, as I said, this gyro frequency is very, very low. And so it's not really observable for the reasons we just mentioned. Actually, the galaxy is opaque to radiation much below a megahertz. And this is 14 hertz. And so you don't generally end up seeing it until you have very strong magnetic fields. So magnetic fields around pulsars, X-ray binaries, which go to Gauss levels, or 10 to the whatever Gauss, then you can start to see it. So you need very strong magnetic fields, typically. So one example of this is that the magnetic field around a neutron star is about 10 to the 12 Gauss. And so, plugging that in, we can estimate where this frequency will occur. And so it actually occurs at about 34 keV. And so this is a spectrum of Hercules X1. Again, in X-ray astronomer units, so it's a little bit difficult to, this is all the instrument response. However, there is an emission line here, which if you fit a model to the data, you see that the model fits the spectrum except here. And so if you add a component for this line, you fit it. Now, it's not super obvious in this data set because this is quite old. And so with more recent, better spectral resolution instruments like NuSTAR, you're able to see this a little bit better, although it still only has 1 keV resolution. So that's just an example of what you see. And the benefit, of course, is if you measure this line, you can infer what the magnetic field is. And so that's nice, right? So the energy of this line will directly relate to this gamma and the magnetic field. Okay, so we can also think of this as having, in addition to emission, we can think of it as having an absorption. In fact, what you ended up sort of seeing here is actually an absorption feature. And so this frequency of absorption from this line, as I said, measures the field strength of the magnetic field. And so if we observe the photon energy, we can relate this photon energy, right, to 34 kilo electron volts. We can relate that to a frequency. And so then we can plug in what our sort of frequency should be, and therefore we end up getting a magnetic field which is sort of consistent. That's in fact how we can measure the magnetic field, or one of the ways we can measure the magnetic field. Obviously, this is for cases where the velocity is not very fast, and so the gamma term is more or less 1. And if the gamma term were higher, of course, then you have to factor that in here. And that would come in as an extra term here. So it would, if you had a gamma that was high, it would increase the magnetic field. All right, so one important assumption through all of this mechanisms is that the energy loss within one loop of this process, one gyration, is a very small amount of the total energy that the electron has. And so that the losses from radiation over that time scale are relatively low. And typically this is satisfied, but there are some individual cases where one has to be careful about that. I can't think of any off the top of my head. They surely have to do with things that are ultra-relativistic more than not, because then the amount of radiation is leaving. Remember, Larmor's formula goes as gamma to some very high power. And so obviously then you can start to see stuff, and then certain lines of sight. There was a question? No? Okay. Just hearing things. Okay, so we can also think, if we want to sort of factor this into the Larmor formula, right, so all we need to do is really, the Larmor formula is given by this. And so, oops, go away. Zoom is blocking me here. So the Larmor formula is given by this. We have a perpendicular component of the acceleration, a parallel component, and we end up having basically an extra gamma of 4 here and an extra gamma of 2 in the parallel component, if there is any. And so, as we mentioned in the case of magnetosynchrotron, magneto-Bremsstrahlung rather, the parallel component is typically going to 0 in our case, so we're just caring about this. And so we end up with a power from the Larmor equation, which if we plug in that the acceleration is equal to this frequency times the perpendicular velocity, we end up with something which looks like this. So here's this frequency, we can expand it out. You know, it's units here, the perpendicular component of the velocity, and I forgot to put a V here. This is velocity, not frequency. And if we move all of these things around, we have something which looks like this. We've bunched a bunch of things in terms of this radius of the electron, to simplify it down. And so this is the total power coming out. If the velocities are distributed isotropically, so if we have a bunch of different velocities, we can define the perpendicular and parallel components with some angle, which we call the pitch angle, and we denote that by alpha. And so obviously there'll be contributions, different contributions from different electrons, moving in different directions. And so we can sum over this. So if we assume that the average perpendicular velocity component, now written as a function of beta, is just this integral over this pitch angle and the solid angle, this integral becomes this thing. And so the total power coming out looks something like this. We can again repackage this, making the assumption that the Thomson cross-section is related to the radius and the magnetic energy density is related to b squared. And so the power ends up looking like something pretty simple, which is just, it's related to the magnetic energy density, which makes sense, b squared, and it's related to the velocity and a bunch of constants. And we have an extra gamma factor here of 2 of gamma squared, which adds in the relativistic component. So if the velocities are relativistic, you know, then we have some power coming in. Okay, so we have this as the angular formula for an individual electron, and we have this as the average one. And so we can ask ourselves a couple of questions here. If you know, this is valid for relativistic particles, does it also describe ones that are non-relativistic? What will happen in a non-relativistic case?
Gamma should be 1.
So gamma goes to 1. Anything else happening here?
Beta.
Well, beta is V divided by C. So V isn't going to 0, it's just going to be low, right?
Mm-hmm.
So of course, the power coming out is proportional to V squared. So if V is very low, you will not have much power coming out, but it will still come out. Does that make sense? All right, so this should hold for mildly relativistic cases, ultra relativistic cases, or even if we're talking about the gyro radiation, the power coming out from the gyro radiation should look like that. What happens if we ended up having protons here instead of electrons? What would change here?
Are more heavy particles, so the contribution is not too high as the same contribution from electrons.
Right. Well, I mean, the mass will change, right? And the mass is hidden in here. So it's hidden in here, but it goes as the mass squared, right? So basically, this power will go. So there's a factor of what, 1,000 between electron and proton. So the power coming out will be a factor of 1,000,000 different. But if you did have a case where you had protons, it would generate this radiation, right? And would cool by this radiation. Cosmic rays can cool by this sort of mean. What happens if alpha is 0? Anyone?
We have 0.
So you have 0, right? So you don't get anything. What happens if alpha is non-zero but very, very low? So you have small pitch angles.
We will have a very little or very small value of p.
It'll be very small, but you can also approximate this. You can use a small value approximation. You can Taylor expand this. And so you can estimate okay, this is, I think, going to be proportional to alpha squared, if I'm not mistaken. Right, so sine alpha goes to alpha. And so the power will be proportional to the angle at which this comes out. Okay, how would we why is it useful to write this in terms of a cross section? Is there any meaning behind it, or is it just because we can?
Because it's a probability study.
Right, well, this is the power coming out from an individual electron. And so we can use some aspects of this to estimate the sort of it ends up having some similarities with other types of processes which do require a cross section. This particular one doesn't require a cross section because it's a magnetic field, right? So it's just a field in the electron. And so there's no true cross section for this interaction to happen. It's just happening. But it allows us to make parallels with other radiation which do require a cross section. So that's really the only, and it just so happens that you can sort of elegantly do this. That's all. But just don't get necessarily tricked by this. That's mostly the point. Just remember that this contains a bunch of interesting variables that we want. Charge, mass, velocity, etc. Okay. So another interesting thing to sort of calculate, and you can do this with virtually any quantity, is to write this quantity divided by the change in that quantity with time, and that will give you a time scale of that change. And so if this particular quantity is the energy of the particle, we can estimate how fast that particle will lose energy through this sort of synchrotron cooling, right? And so we have the energy of the electron, which is just this, and we have the power being radiated out, which is just this in an average sense. And so we can divide out some of these numbers and calculate this. And so we have numbers for all these things. Remember, this is magnetic field, so we pop it back out here. One of the gammas divides out, and so we get that the time is related to the magnetic field squared, the speed, and is sort of 25 years if we calculate it out in terms of years. And so if we look at the values around a black hole, for instance, a black hole might have 10 to the 3 Gauss. It might have an average electron speed of 10 to the 3 coming out of a jet. And so plugging these in, the synchrotron cooling time scale is actually really quick. It's of the order of 1 second because of the extreme nature of this. And so what this, of course, means is that you need to constantly, the black hole needs to constantly inject energy and have a mechanism for accelerating, constantly accelerating the electrons in order to keep up this stream of electrons coming out. If we take that same electron and we now have transported it out into the radial lobe, right, which is 100, let's say 10 kiloparsec, 100 kiloparsec away, the magnetic field in that larger region now is much lower. So the magnetic field is only about maybe 10 to the minus 5 gal, similar to the Milky Way field. The speed might still be 10 to the 3. And so you could again estimate the cooling time. And because this is 8 orders of magnitude and this is squared, this is a huge, huge difference. So magnetic field makes a very strong difference in how much radiation comes out and how fast the particle will lose energy. And so a particle in the radial lobe will take roughly 250 million years to radiate that energy, right? So it's pretty significant. It's kind of it's a little bit smaller than, a factor of, let's see, 5 less, no, is it right? I can't do math at all now. So yeah, it's about a factor of 50 less than the age of the universe. And so, you could have, if you see a radial lobe, that it's, it had to be produced and sort of has a lifetime of that. So it wasn't always there. And if you don't see a radial lobe, or if you see that the jets have moved, you can actually estimate how fast that happened because of things like this cooling time. Okay, so we can then think about how to calculate the spectrum for the cyclotron or the cyclotron or the synchrotron case. And so it's useful to think about what's actually going on here. So we have our helical motion, right? And what's going to happen is that this radiation is going to be propagating in the direction perpendicular to the helical motion. And so it's going to be propagating in this direction, and depending on the velocity, it will propagate. It could propagate isotropically, but as you go faster and faster, the beaming effect will start to beam that radiation into a cone. And so most of the radiation will come out in a cone. But this thing is moving. And so the cone is moving with respect to the line of sight. And so there's only a fraction of the overall curvature when we see it, right? So we see this radiation coming towards us for this period of, or this segment of the arc, which we can define as delta theta, when it goes from point 1 to point 2. And then if it moves beyond that, this cone moves out of our line of sight, right? And before this, the cone wasn't in our line of sight yet. And this angle here is roughly equal to 1 over gamma. Does this make sense? Hopefully. And so this period overall is related to this, right? And so we have the radiation coming out will be, the pulse radiation, it will be confined to a time interval here, which is actually smaller than the gyration period. And so what this means is that the spectrum will be spread over a much broader spectral range here than just this, order of WB divided by pi. And so this is a characteristic of synchrotron radiation. So rather than an emission line coming out, which is what happens for gyro radiation, you end up getting a broader spectrum which is broadened. And the degree of broadening depends on the speed. So we can estimate what this is, right? So the observer here is going to see this pulse between points 1 and 2. And so this, we're going to see it between, this emission cone is going to have an angular width of roughly 1 over gamma. And there's going to be a curvature path length, delta S, along which we can compute a radius of curvature. And so the radius of curvature we'll define as A. Sorry, it's also the same letter as acceleration, but this is the radius of curvature. And so this is going to be this path length divided by the change in angle. And so based on this geometry, here we have delta gamma is going to equal 2 divided by, delta theta is going to be equal to 2 divided by gamma. And so we can plug in this here, and we can say that this change in path length will be related to the radius of curvature times 2 divided by gamma. And so we can then plug in our equation of motion here. And so we had this change, this acceleration was proportional to the cross product of velocity times the magnetic field. And so for delta V, we have, it's going at a constant velocity for the moment, and multiply that by the change in angle. Delta S will be related to V times delta T. And we can then map this out. So plugging in, so equating this and plugging in our different values here for V, the constant V, and this change in angle, and plugging in delta S for delta T, we end up with this change in angle as a function of this, which is also the curvature, the radius of curvature. I cannot talk anymore. Is roughly equal to this, where we've now incorporated the pitch angle here as this difference here, and this V ends up going on the bottom because there was a couple of extra V's here. So this radius of curvature we can estimate is based on the velocity, this gyro radius, or gyro frequency rather, and the pitch angle. So this is all just a substitution of math for the moment. And so this thing ends up differing by a factor of this from the radius of a circle of projected motion on a plane normal to the magnetic field. And so we can think of this as this delta S is going to then look like this. So we can plug in our sort of values here for this, and we end up with this extra factor of delta, or sorry, yeah. Okay, so this thing is related to the velocity, is related to the velocity here too. It's related to our gyro frequency, so our magnetic field principally. But there's another factor of gamma here and our pitch angle. Okay, and so what we want to ask now is this change in delta S. This is going to be related to and I think, again, this should be velocity. I don't know why the italic version of this makes it look like a frequency for some reason. So this thing, again, we can relate this to time 1 and time 2 from here. So time 1 to time 2. So this will be the velocity times this time difference. T2 minus T1. So that's just what this is. And so we can then plug this in, that this difference in time is related to this. All right, so the fraction of time that we see it is related to gamma squared here, effectively, and the pitch angle, which makes sense. If the pitch angle is 0, then we really never see it. So the time is infinite. So this time is in the frame of the electron. And so now what we want to do is measure arrival times. Aha! Remember arrival times, they're coming back to us. So I'm going to move this over here just so it's a little bit cleaner. So we can then have our arrival time 1 and our arrival time 2, and we want, obviously, in our frame, the observer frame, the change, the difference here will be our delta TA, arrival. And so this thing will be less than this thing by a factor of this. And so we can plug in this sort of arrival time, and we have this thing, but we have this extra factor here, which ends up being related to the Doppler effect. And so we can rearrange these things and look something like this, right? So this is just 1 over gamma squared. And so we can move it down here, and this will be gamma cubed. Sorry, it's 1 over 2 gamma squared. Okay, so that's our delta arrival time, and it's strongly dependent on gamma. And so the higher this is, the shorter this is. Okay, so we find here that what we observe are pulses that are a fraction of the gyro period. And the pulses are smaller than the gyro period by a factor of gamma cubed, right? And so the spectrum will then be broadened by this gamma cubed factor. And we will have cutoff frequencies which will occur at around 1 over delta T arrival. And we can define this cutoff frequency. So we plug in our value for delta T arrival, it's this. And so we can estimate a cutoff frequency, which is related to the magneto-Bremsstrahlung frequency, gamma cubed, the pitch angle, and this extra factor here. Or we could turn this into an actual frequency by just dividing by 2 pi. Is everyone with me so far?
I don't know if I listen wrong, but omega b is the synchrotron orbital frequency.
Yeah.
Okay.
Way back here, I don't know why Rubicki and Lightman choose B for this, other than B from magnetic field. But it is super confusing with Bremsstrahlung, which is something completely different. So yeah, I think if you remember it as magnetic field, it's the easiest thing to do. But yeah, it's the synchrotron orbital frequency. Okay. So
sorry, I have another question. Because gamma is divided by velocity squared over c squared, or not?
Oh, I'm sorry. Oops. I lost it.
And
where are we?
The common definition is with velocity square over c square, or not? Gamma. And here we have velocity over c.
Yeah. No. So this is why you end up with this extra 2 here.
Oh. Okay.
And this is approximate. So it's a.
Oh yeah. Yeah.
And hence this is approximate. So you do a Taylor expansion, you expand it and all that. good stuff. Yeah. Okay. So what this will end up looking like is it's going around, we don't see it, then we see a spike, then it goes around a little bit longer for another pass, then we see a spike, and so forth. And so we see pulses, right, that look like this. So the pulse might have a very narrow width and then a long delay as it's emitting in other directions, and then it will come back and we'll get a pulse and so forth. And so this is very typical of, you know, emission from an electron which is gyrating around. So we have these narrowly spaced pulses. And so this actually looks like a comb in sort of its regularity. And the sort of, you know, the numerical values here are actually ones for a typical emission of a cosmic ray electron in the magnetic field of the ISM. Just to give you an idea of the pulse time, this is the arrival time, right, that we calculated here. And then this is the typical cyclotron orbital frequency, or the cyclotron gyro frequency. So that's to the order of 1,000 seconds. And of course, plugging that in, you then get an arrival time, which is for this particular gamma, which is pretty high. And this particular magnetic field ends up being about 10 to the minus 10. So this, I mean, this is a very narrow pulse, and then a very long gap, and then a very narrow pulse, right? And so the spacing of these pulses is sort of related here. But it's gamma divided by the gyro frequency in nu values, so divided by 2 pi. So this particular sort of function, if we take a Fourier transform of this, we will get out the spectrum, right? Because this is the time variability of this power. And so if we Fourier transform, we'll get out the spectrum. Now, instead of calculating this Fourier transform directly, we note that this is basically a pulse train. And so this pulse train, each individual pulse is very similar. And we can then convolve the Fourier transform of this individual pulse with the Shaw function. And when we do that, it simplifies the math, but we end up getting out the same thing. So we'll return to this later. Okay, so thinking a little bit more about this, we have we want to actually calculate what the radiation coming out is going to look like from an individual pulse. And so we can think about the electric field as a function of theta. And we then think of it as through a combination of gamma theta. So that's the angle that it's coming out at. And so this tells us basically about how much beaming is going to happen. And so we can then write this electric field at variance as a function of time as some functional form of gamma and theta. And so as before, we can write theta in terms of the sort of path length and the radius of curvature. And we can write time, the arrival time, as this path length divided by velocity times our Doppler shift. And so in doing that, this functional form can be translated to something which looks like this. And this thing is just proportional to this cutoff frequency times time. And so this thing will then be a functional form of the cutoff frequency times time. And that allows us to kind of understand how this thing was going to vary with time. So it's just going to be a function of this cutoff frequency and time itself, which is good. We don't know how to normalize it. We don't know anything about it. But we just know that, you know, we can dump this into some sort of dependence on these two variables. So a trick we then can play is to know that if we have something which is proportional, and so we have, you know, this E field as a function of frequency will be proportional to the Fourier transform of this function, whatever the hell it is. And so we can then do a substitution here where we substitute this for any variable, and we have a functional form which looks like this. And we can also remember that the power coming out as a function of solid angle and frequency was proportional to the square of this thing, right? Based on the Larmor equation before. So, or not the Larmor equation, the pointing vector, the pointing flux. And so we can integrate over the solid angle, and we can divide by the orbital period to get some sense of what this is going to look like. And this is all just very hand-wavy, just trying to understand the functional form of how this is going to look. So this thing here is equivalent to some orbital time times this power coming out as a function of frequency. This thing is equal to some power as a function of frequency, and this thing is equal to some normalization constant times some functional form, which we can relate to the cutoff frequency. And so we now are starting to get where we can relate these things back and then sort of magically figure out what the normalizations are for all of that. And we'll do this in much more rigorous detail later, but the idea is just to give you a sense of how these things relate to each other. So recall that we had the power perpendicular as a function of solid angle, and parallel as a function of solid angle, and perpendicular, and you know, they're very nice ugly things, which gave you the beaming, right? And so we can use that. And so we have here that if we integrate this thing over frequency, we'll get the total power that comes out. And so we can plug in our functional form here, integrating it over the frequency, and we can make a variable substitution here where we say this is equal to X. And so we have something which looks like this. So the power is proportional to our cutoff frequency, some normalization which we need to define, and then this some integral over a weird function, which is a function of frequency. So we have no idea what this is. It's a dimensionless value though, which is useful. And we can then figure out the dependence of C1 on all of our physical parameters. And so before we had that the power was related to this. And so what we can say here is that this, we know that this cutoff frequency is equal to this. And so the power is going to look something like this. And so this normalization will have some dependence on magnetic field, some dependence on the pitch angle, and a few constants, and that's it. And then whatever this functional form is, which still need to figure that out. And the choice of this normalization to have this is in anticipation of how we're going to have to transform this, and we want to be able to transform it and have this thing, which is a function of orbital frequency into real frequency, work out. So we have this extra 2 here, for down the line when we want to remove it. Okay, so you're still very lost here because what the hell is this thing? So we're not going to get there yet, but we want to think about how in this functional form, what is kind of interesting is that there's no gamma factor in here at all yet. It's all sort of hidden in this functional form, but the normalization doesn't have anything there. So we also, other than the fact that there's an intrinsic gamma squared factor in here, but that's again hidden in here. So typically you can estimate a spectrum as being a power law over a very, very short frequency range. So you can imagine the black body spectrum, right? If you take it over a very short range, you can estimate that as a power law. And you can just do that piecewise, and every portion you can estimate with a power law. And you'll do a decent job as long as the frequency range is small enough. And so what we can say here is then that this power is going to be proportional to the frequency to some power index, some spectral index. And we can then approximate what the shape of this thing is just by the spectral index as a function of frequency, for instance. On the Rayleigh-Jeans portion of a black body, S would be -2. Right, so the frequency would increase squared. For Bremsstrahlung here, what we would do is we would input a velocity distribution for the relativistic electrons, and this would dictate what the spectrum looked like. And so we can think about the distribution of electrons as giving rise to as having some impact on what the functional form of the spectrum will look like in its ensemble form, right? Not just one particular electron, but an ensemble of them. And so imagine we have a number density of particles here. They have energies between E and E plus dE. We can transform this energy into an equivalent of gamma and gamma plus dE gamma. And so we could then express the number as a function of energy as this number is a function, per energy as some constant times the energy to some power dE. And over a very small range in dE, this works, right? This is again just approximating the distribution by this power law. We can do the same thing for gamma, right? Just transforming this. So this value C is how we would normalize everything. And then we would just have the slope be related to this P. And this is a very generic way to sort of set this up. The C here could vary with pitch angle, it could vary with magnetic field, etc. And so if we can think about the total power coming out, this is going to be related to the number density of electrons and obviously the magnetic field and their distribution in terms of their pitch angles. And so we can then think about this functional form, rewriting it. So this is the functional form for an individual electron. And remember, we can multiply the functional form for an individual electron times the number of electrons over a small range in energy so that they're all roughly equal. And then we can do the integral to get the total amount of power that's coming out. So hopefully that makes some sense. So the individual power times this distribution of number density over a small range in dE or d gamma in this case. So we're just integrating over this small range times this constant. And so this thing is going to be proportional to this thing. And this is a proportionality. We can fold everything back into the constant, more or less. We can make a variable change. And so we end up saying that this thing here, which is gamma, we can notice that let's say we have a variable change where x equals omega divided by omega c. omega c is proportional to gamma squared. And so we can make a substitution here for those things. And so this thing will end up being proportional to this ugly looking function. And we're no longer, we're not integrating over the frequency, we're integrating over the energies. And so the energy comes in from this term here. So it's a little bit complex, but we move out these different values here. And what we want to do is take the integral of this thing, which is integrating over this distribution more than anything else. And so we have some frequency dependence, which is dependent on the power law index. And then we have some functional form here. We don't know what this functional form is. And then we have some dependence, again, on the frequency to some power law. So here we can say that the limits x1 and x2, they correspond to these limits here, and they depend on frequency. And so we can note that if these limits are wide enough, we can approximate x1 is 0 and x2 is infinity. And then this integral will roughly be constant. And so then this, if we integrate over the entire energy range, we have something which is proportional here. And this thing is just a constant in the end. And so this proportionality should work out. This thing here, p minus 1 divided by 2, we can make another variable substitution. And this s, which is the spectral index, is then omega to the minus s. And we come back to, where was it? Here. So we generally have something which looks like this. And we've moved almost everything into a constant here. And the fact that we have to do this in very short intervals, because this thing directly reflects back on what this is. Right? S equals p minus 1 divided by 2. And so if this changes, this changes. If this is constant, then we can integrate over that region where it's constant. Hence, we kind of have come back to this situation where as long as we have small enough intervals, we can approximate this as being constant in between them. And so this sort of circular argument holds, at least. Okay, so this treatment, while very hand-wavy, gives you rough intuition about the functional form of the power that's coming out, how the power is going to vary as a function of frequency. So the angular distribution here is always going to lie within 1 over gamma. So it's a cone on the sky, and it will be radiating, right, and have this time dependence, which we haven't addressed yet. This is for the single particle spectrum here extends up to some frequency and then has a cutoff. Then the power law distribution of an ensemble of particles will have some spectral form which looks like this. So those are the basics of synchrotron radiation. And the idea behind presenting it in this way is to not get bogged down in the very gory math that we're about to embark on. So it is not pretty. The sort of functions you have to work with. So the idea behind this is just to, in a very hand-wavy sense, get an understanding of what the frequency functional form is and how everything else is kind of a constant. And the constants are going to be obvious things. So it's going to depend on the magnetic field. It's going to depend on what you do for the pitch angle. And it's going to depend on gamma in there somewhere. Okay. I think I'm out of time, so I'm going to stop here. I was actually one slide away from being done. Right, so, oh, I'm way out of time. Oh, you guys should have stopped me. Jeez, okay. I'll come back to this later. So, yeah, okay. Any doubts, questions? Okay, sorry for that. I get lost sometimes. So, trying to explain stuff. Okay, so I'll come back and explain this later. All right, see you guys on Wednesday. No, Monday. Next Monday. And yeah, we'll have office hours on Friday. Homework's due on Monday. Sorry about that. What else? Oh, one thing I want to ask you is if you would prefer to have the test on Wednesday or on Friday of that week. So think about that. In terms of time, I'm not sure. We'd have to do a doodle poll to see, or maybe stagger it or something to see if that worked. In theory, we could start it during my office hours and you have more time. The benefit would be that you know there's no classes before or after or anything like that, and you have a couple extra days to study. I don't really care, but it needs to happen before you go on vacation. So think about that. We'll talk about it on Monday. Okay. Bye.
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 Bye.